Hi everyone. Welcome to today's COMET Plus webinar, which is going to be given by Jean-François Smekens. But before JF starts his talk, I would like to quickly advertise the next COMET Plus webinar, which is next Wednesday on the 1st of November at 4 p.m. UK time, during which we'll hear from Nicholas Castro-Perdomo at Indiana University, who's going to be talking about crustal deformation in the Mediterranean and the Middle East. So our speaker today is Jean-François Smekens, who is a postdoctoral researcher at the University of Oxford. And he'll be talking about the research he's done in the last few years in Oxford, which has involved using ground-based techniques to monitor emissions of ash, aerosols, and gas from volcanoes. The talk's going to last for around 40 minutes, and if you have any questions for JF, then please put them in the chat and we'll come to them after the talk. Over to you, JF.
Thank you, Isabel, and thank you, COMET, for having me on this webinar. So as Isabel said, my name is Jean-François. I'm currently a postdoc at the University of Oxford, and I'll be showing you some work that I've done here over the past 4 years now with collaborators from Oxford, from the University of Manchester, and of course, our collaborators in the field, INGV in Catania and in the Met Office in Iceland. And so the topic of the presentation today will be how we can use OP-FTIR measurements to gain insight into the formation of aerosols, and especially in young volcanic plumes, which we'll define what young means shortly. And so briefly, I'll give a quick introduction of motivations and what OP-FTIR does, and then go into two different parts of the talk. The first part will concern emission measurements, which is a kind of an alternative, more flexible geometry for OP-FTIR, and how we've applied retrieval of particulate species to that emission measurements. And then in the second part of the talk, I'll talk about efforts to then apply those lessons learned there into transmission measurements, which are the more traditional way in which OP-FTIR are acquired, and whether we can retrieve particulates in those geometries. And then hopefully I'll leave you with some take-home messages about the usefulness of these measurements. Quickly, if they, aerosols in volcanic plumes. So if you look at this picture here on the right of the gas plume from Holaron in 2014 and 15, it should be fairly apparent that aerosol form very quickly as gases are being exhaled into the atmosphere and as the plume condenses. And so the composition of these aerosols has been a topic of great interest for the community, and it's a very complex situation, and the composition depends on a lot of parameters. But the primary phase is often a sulfate phase with a binary solution of acid, sulfuric acid, and water, onto which then other elements can be incorporated, such as halogens, but as well the aerosol phase is a vehicle for trace metals, which some of which may be very harmful for human health. And as well, ash is often also considered as an aerosol in those plumes, particularly the finer fraction of volcanic ash. And so there's very great interest in understanding the composition, how these aerosol forms, how they evolve as they're emitted into the atmosphere, because there's a series of impacts. Most notably in the troposphere, when those aerosols are emitted, there's a series of health hazards associated with respiratory hazard, mainly on local and regional populations. And then if large amounts of those aerosols are injected into the stratosphere, there's also radiative forcing effects, and they have a great impact on climate, possible impact on climate on more global scale. But as well, arguably, there should be interest from the physical volcanology standpoint, because the composition of gases is used to infer some properties of the underlying plumbing system and storage, and then the exsolution of gases during ascent during volcanic eruptions. And so this relies on accurate quantification of what the composition of the gases are. And so the presence of an aerosol phase and just how much of this gas phase goes into the aerosol phase can introduce this biases when looking at gas composition at various points downwind. And so understanding how quickly they form and how the magnitude of those biases and whether they're significant or not is also has impact on then the interpretation that we do in physical volcanology with those gas composition. So there's two types of measurement techniques to look at aerosols. Remote sensing is a very powerful tool. There's been many studies of aerosol, volcanic aerosols from satellite in the infrared, the UV, the visible, and as well weather radars are commonly used, especially when there's a significant fraction of ash in those plumes. So that's usually for more mature plumes that are injected higher up in the atmosphere and that are traveling far away from the vent. For a near source sampling characterization, so a few kilometers from the vent, there's been a lot of studies on direct sampling. So, for example, using filter packs and particle counters. And of course, the emergence of drone has made all of this even better because we can now deploy those sensors closer and closer to the vent. And the recent eruptions in Iceland are a perfect example of how that's been done. But I'd like to talk about what OP-FTIR here can offer. And so that's kind of combining the near source aspect with kind of the remote sensing aspect. And so for those of you who may be unfamiliar with OP-FTIR spectroscopy, FTIR instruments essentially measure the radiation of light at wavelengths ranging from 1 to 50 microns. And within this wavelength range, there's a number of gas species that have diagnostic features and that produce absorption at certain frequencies or wavelengths. And the strength of these absorptions can be scaled in retrieving the amount of gas that is present along the line of sight that the measurement is made on. And so rather than looking at emission rates like a DOAS instrument might do, then we look here at gas composition by presenting the ratios between two gas species and using that to infer the gas composition, such as is presented in the example here in the top right from a paper in 2015, looking at the individual composition of gases from individual vents in Etna. And so the traditional way in which this is done is by attaining transmission geometry. So this is using a strong source of infrared radiation and placing the instrument in such a way that the plume is in between the source and the observer. And so this can be achieved in several ways. The first one on the left is to use the incandescent eruptive material itself, and this is what I refer to as direct line of sight. And it will be the subject of part 2 of the talk. And so this is best suited for effusive or mild explosive activity. Another way is to use an active source, an artificial light source, which is best for grounded plumes on crater rims, for example. And then a third way might be to then use the sun or the moon as the source of radiation, which is more appropriate for plumes further downwind or plumes that are higher up in elevation. And so in the first part of the talk, I think I'd like to talk to you about an alternative geometry, which is these emission measurements. So this is a subject of a paper that was published earlier this year. And so this opens up the possibility of continuous measurements. And we have developed a fast algorithm to do near real-time retrieval of SO2, ash, and sulfate aerosols, so the particulates as well, from one spectral window. And so this emission geometry is depicted here in this sketch. And essentially, because we are not using an independent source of radiation, but we're measuring the light emitted by the plume itself against a colder sky background, then the geometry is not quite so constraining, and it can be deployed in a more passive manner. The method does require radiance calibration with temperature-controlled blackbodies, which is not available in all instruments, and the wavelength range is then limited to the thermal infrared window between around 8 and 12 microns. However, it does open up the possibility of quantifying the particulate species. And so we've developed a forward model, which is a simplified model with a 3-layer atmosphere. What the model is replicating is a radiance difference between a measurement taken with the plume in the line of sight and a measurement taken in similar condition but without plume in the line of sight. And this is done to emphasize the spectral signatures of the species of interest, the volcanic species. And so this is all packaged into a Python software, which is available as an open source software on GitHub. And so this is a sped up movie of a data processing session in which we can see the spectral information displayed in the top panels. And then the middle panel shows a time series of the quantities being retrieved. And the bottom 2 panels are some ratios of some of the quantities that we might be interested in. For example, the SO2 over silicon tetrafluoride ratio, and then the SO2 over sulfate aerosol ratio. So when retrieving particulate matters, there's some dependency of the spectral features of those particulates on both the particle size, which is here illustrated in the left panels, and the chemical composition, which is illustrated in the right panels. So the sulfate aerosols are in green in the top, and the silicate ash is in gray in the bottom. As you can see, both particle size and chemical composition introduced some changes in the expected spectral features of those aerosol species. However, retrieving both at the same time is not easily done. And so what we've chosen to do in the remainder of the talk is to fix the chemical composition by making some assumptions, essentially, and then retrieving the particle size during our retrieval as a free parameter. So we've deployed this method in 2 measurement campaigns on Stromboli volcano. And so those of you familiar with Stromboli will know that it's a great test laboratory for a range of new techniques and methods, because it produces persistent activity, and it has done so for many decades and centuries now. And this activity consists of passive degassing, but also some more explosive events, which are characterized as type 1 and type 2. Type 1s being bubble bursts with essentially gases and ballistics, and type 2 being larger events with significant ash content. Now, on top of that, there's also a series of paroxysmal eruptions or larger eruptions, which are not the subject of this talk, so I won't be getting into that. So we went to Stromboli in two different times, in 2019 and 2021. First time we had a direct view of the craters, and we deployed a drone, a UAS, to collect an ash sample. And in 2021, the plume was in a different direction, drifting in a different direction. And so our ideal viewing location did not have a view of the craters. However, we did perform some simultaneous measurements with UV spectrometer for validation purposes. And so these are the results of this validation exercise. And here, the top panel shows a time series over approximately 4 hours of retrieval with the infrared methods that we've developed in red, and the UV method in blue. And so this is a time series of the column density of SO2. And in the bottom, the colored bar charts are in gray, the ash column density, and in green, the sulfate aerosol density, and in blue, the total of the two. And so what we can see is that there's a reasonable agreement between the two methods with some notable differences. And so in the bottom, there's a zoom of the start of this data set in figure B here. And so what we can see is that there's some times where the methods don't agree with each other, and that is usually when there are large amounts of particulates within the plume. And so I think this can be explored further to try and understand the strength and the relative strength and weaknesses of both UV and infrared, and may perhaps inform and converge towards better measurements in the future. But now if we move to the data sets with the field of view directly above the vents, what we have here is a time series capturing several events over the course of approximately an hour. And we've captured both type 1 events and type 2 events drifting in the field of view of the instruments. And the model correctly identifies the type 1 events with no discernible ash, and the type 2 events that do contain high ash content as well. What we're able to do then with this data set is to create, to look at the ratio between SO2 and the sulfate aerosol phase, which here is presented as a mass ratio between SO2 and the mass of sulfate aerosol, ranging between 40 and 100. And however, this ratio does increase fairly significantly during those explosive events, and this is denoted in those data points on the bottom right plot of the scatter plot here. So then what we've done is to move the field of view a little bit further away from the source to distances of approximately 1 kilometer in terms of the plume transport, and look at the ratio and how it varied then. And so what we found is that this ratio then decreases quite rapidly as we move the field of view downwind. And so the potential mechanisms that could explain this this change in ratio is the oxidation of SO2 to sulfate. However, this is a very short time scale. We're only talking about a minute or so of plume travel, perhaps less. Or it could be the condensation of water onto the existing sulfate aerosol droplets, because we're not retrieving composition. We can't know if the acid is being diluted, but the mass of the droplets is increasing. And this is consistent with the observed increase in the retrieved sizes of the sulfate aerosol. And so this is what I attempt to show here in these plots, where you have the particle size distribution over the whole data set plotted in gray for the ash and in green for the sulfate aerosols. And so the top two panels are for the proximal data set directly above the vent, and then the bottom further away from the vent. And what we can see is that for the ash, we have a slight decrease in the size of the measured ash with distance. And we can see that the large fraction, which was identified in the sample from the UAS, which is here plotted in a yellow shade, is not captured in our retrievals. And this is not really surprising, given that the sensitivity of the infrared spectroscopic method to sizes greater than maybe 15 or 20 micron is probably not the best. And so this size fraction is not really measurable with this method. But we do capture the finer fraction of the aerosol quite well. For the sulfate aerosol, there's the opposite, which is an increase in size with distance. And so in summary, we've developed this fast quantitative model to retrieve 3 different species of interest simultaneously with a method that's comparable to what is being done for a satellite instrument, and which offers a fast processing time. So we haven't done this in near real time in the field, but theoretically it is possible because the processing time is shorter than the acquisition time of the data. And using these data, we can quantify physical and chemical processes that happen during plume transport, including ash sedimentation and rapid aerosol growth. And so this enables continuous monitoring, because this can be deployed in a passive manner and be used in nighttime, and allows us to then investigate high frequency variations over more continuous data sets. And so in the second part of the talk, I'd like to try and take those lessons, and this is a subject of a paper we hope to submit really soon, to transmission measurements, so more traditional open path FTIR data, and our attempts at a quantitative algorithm to use in uncalibrated data. And I'll try to show you that we've seen some temperature-dependent sulfur partitioning between the gas and aerosol phase in very young plumes. So the motivations for this work is that in direct line of sight measurements, typically the longer wave number portion of the spectrum is used, so over 2000 wave number, to look at gases in transmission. And the thermal infrared window is either not acquired or not often looked at. However, there's been qualitative recognition, certainly, that there are sulfate aerosols, and I'd like to point out one effort by Celito et al. In 2019 of a quantitative effort to look at those in sulfate aerosols and SO2 in active source with an artificial light source. And so adapting this retrieval algorithm for uncalibrated data is not trivial, partly because it does involve uncalibrated data, but also because the scene is thermally quite complex. And so in order to do that, we've simplified the geometry quite a bit and made some assumptions about limiting the background polynomial to a maximum degree of 3, essentially assuming a linear response of the detector. And as well, extracting gas temperature, so information about the gas temperature from spectral windows outside of the thermal infrared. And so in this way, we hope to attribute the broader changes in spectral features of the background to the aerosol species. So we applied this to a data set that was collected during the Fagradalsfjall eruption in Iceland in 2021. So this eruption was the first in almost 800 years on the Reykjanes Peninsula. It has been followed since by 2 subsequent eruptions in the same location. And it saw the emplacement of a quite large lava flow field and at the same time some fire fountaining activity at the main vent or vents. Our measurements were taken during what has been designated as phase 4, which was characterized by a cyclic diffusion and fountaining at the vent on periods of about 24 hours when we were there. So we've acquired UV traverses in an effort to quantify the intensity of the degassing, but also OP-FTIR data set. So I'll focus only on the direct line of sight data set, and we've also acquired solar occultation data sets, which we haven't quite processed yet, so I won't be talking about those. And so the UV traverse measurements were a series of repeated traverse during across multiple eruptive cycles. And this was done to establish a time series of emission and look at how it related to the activity at the vent. And somewhat unsurprisingly, of course, the SO2 emission rate kind of scales with the intensity of the harmonic tremor that was measured, which supports the fact that those cycles were driven by gas rising to the surface. And so the direct line of sight measurements are a relatively simple process compared to the emission measurements, for example. So it consists of a simple 2-layer model with a plume layer that contains all the volcanic species close to the vent, and then an atmospheric layer that contains all the atmospheric gaseous species and covers the entirety of the line of sight between the measurement and the source. However, as this sketch hopefully illustrates, the situation, the reality of the situation is quite more complex than this simple model. There are gradients involved, of course, in here, most particularly gradient in temperature in close proximity to the source, to the infrared source, whereas the model assumes a single temperature for that layer, which is definitely not the reality. As well, there are some complexities along the line of sight, both in terms of temperature and in terms of expected gas concentration that could be introduced by the presence of a lava flow there along that line of sight, and potential outgassing, diffuse outgassing from the lava flow itself. And so one consideration that must be taken when looking at retrievals in the thermal infrared is the radiation coming from the hot gas itself. So we're back to a little bit of the emission problem here. Whereas this may not be such a big problem when looking at longer wave numbers. When looking at thermal infrared window, then it does become quite significant. So here, those 2 plots are simulated transmittance for hot gas. So here at 500 Kelvin in front of a lava source at 1500 Kelvin. And so these are two features of the SO2 gas. On the left, the thermal infrared feature, and on the new one feature, sorry. And on the right is the nu 1 plus nu 3 feature, which is at longer wave numbers. And what I've tried to show is then the relative contribution of the emission from the gas itself, which is depicted in yellow, and then the change in the apparent transmission that is generated by this new emission term. And while you can see that at longer wave numbers, this is essentially negligible, it makes very little difference and is within the noise of the measurements themselves. At thermal infrared, radiation is no longer the case, and it kind of has to be accounted for. And so we've added an emission term to our model to reflect that. However, that also supposes that we should know something about how hot the gas is compared to the source. And so to that end, we've done a temperature fitting using the nu 1 plus nu 3 absorption feature of SO2 to retrieve both the column density and the temperature at the same time, because this feature is, the shape of it is highly sensitive to changes in temperature. And so we observe a wide range of temperature here. And remember, this is not essentially it's the temperature of the gas, but it's an amalgamation of a gradient. So it's a single number representing a very complex situation. However, we observe some very rapid fluctuation reflecting the dynamic degassing nature of the source. And if we look at plot number C here on the bottom right, which is plotting the column density retrieved assuming a single temperature at the mean of 450 K versus the column density retrieved with a variable temperature, we can see that there can be some significant errors introduced by simply using a constant temperature. And so hopefully we get better gas ratios in that way by fitting this temperature. So then we can propagate this temperature to the retrieval of other volcanic gases and then use these ratios. Here, all of the ratios are plotted against the column density of SO2, which is used as our kind of measure of the intensity of degassing. And then create a gas composition, overall gas composition, which is presented in the table here. And I'd like to draw your attention particularly on the middle plot here, plot C, which shows an offset in the HCl. So the intercept should be at 0, 0, it isn't. And so this may reflect a potential source, low sulfur source, which could be represented by the degassing of the lava flow. However, it also could be a systematic misfit, and the magnitude of this offset is not hugely significant. So it's hard to say whether it's misfit or contribution from the lava flow, really. But those ratios are consistent with values routinely measured by the Met Office in the field. And the carbon to sulfur ratio is also very consistent with what was measured at the start of the eruption. And so confident in that, we've applied this temperature information to the retrievals in the thermal infrared, and we've adapted the software. And so this is the same kind of display that was presented before, and I'll just draw your attention to that SO2 over sulfate. In this case, now it's a molar ratio that is being acquired as the data set is being processed. And it outlines a very narrow kind of relationship here. And so this is presented in this figure here, where we have the sulfate aerosols in the top 3 panels and the water aerosols in the bottom 3 panels. And so this is the result of, we've tried retrievals using sulfate aerosols, water aerosols, and silicate ash, and every combination thereof. And the best fits were produced when using an external mixtures of sulfate and water aerosols. And so these two plots show on the left the partition between the gas phase and the aerosol phase. In the middle panel is a time series of the ratio between gas and aerosol over time. And then on the right is an evolution of the size of the aerosol according to their the intensity of the the column density. And so all of these data points are also colored according to the retrieved gas temperature in the new 1 plus new 3 window. And so what I hope to draw your attention to is that we've defined a fairly narrow relationship, a very narrow scatter between the gas and aerosol sulfur phases, so SO2 and SO4, with a ratio that has a mean of 160, but a range between 100 and 250, and that presents very fine droplets in the more concentrated plumes. The water aerosols, on the other hand, have very large droplets, and the gas versus aerosol plot is anti-correlated. But what I hope you can see is that all those characteristics appear to be temperature dependent. And so the ratios between gas and aerosols, for example, are temperature dependent. And so what we postulate might be happening is that we're observing the rapid formation of primary aerosols as the gas cools down and condenses. And so on this plot here, the x-axis is the gas to aerosol ratio for H2O, which is taken as a measure of plume condensation, with larger values on the left representing mostly gas plumes, and then as we move to lower values on the right, then the plume is condensing. And so as we can see from the top to the bottom, the gas temperature is decreasing. That's as expected, but then the aerosols are essentially growing, both the sulfate and the water aerosols. Sulfate aerosols do remain within a narrow 1 to 2 micron range, and the water aerosols span a much wider range. So this we think might be showing that the sulfate aerosols are condensing, and then the water is condensing around them. And then the bottom plot here, so it shows the SO2 to sulfate ratio, which is showing a clear negative correlation and a decrease as the plume condenses. So this also reflects the fact that the sulfur is going preferentially then back into the preferentially into the aerosol flames. So the aerosols are condensing. This is at least what we suggest might be happening here. As well as the temperature dependence, we've shown some temporal evolution over the course of the data set, both a gradual trend and some individual pulses. But so this phase 4 was characterized by those repeated cycles, and the data set we acquired, short as it may be, it's only 30 minutes, it fits within a longer cycle and a period of ramping up of the activity. And so even on that short 30-minute timescale, we can see some gradual changes within our data set in several key parameters of the gas and aerosols. And they seem to scale with the intensity of the harmonic tremor. So we see that the measured intensity at the instrument of the infrared signal increases, which reflects kind of a more intense source. And as well, both the gas temperature and the column density of SO2 seem to increase generally as well, which reflects kind of more concentrated, hotter plumes being emitted, or kind of a more vigorous degassing source. And as this happens, then the SO2 to sulfate ratio then increases. And this may be a reflection of the more vigorous intensity of the degassing, which kind of like promotes faster cooling and then freezes this kind of early aerosol formation process in place, and allows fewer of the sulfur to then end up in the sulfate phase. All the while, the gas composition elsewhere for other elements does remain fairly stable. There's a slight increase in the carbon to sulfur ratio, which may reflect some fractionation between the main vent and the lava flow. However, the increase is fairly small and can't be really taken as significant as such. The sulfur to chlorine ratio then remains fairly stable, and as does the sulfur to fluorine ratio. And so in summary, I hope I've shown that quantitative retrieval is possible for those traditional geometries, if assuming a set of reasonable expectations in terms of the response function of the instrument and the plume geometry. However, there's a need to characterize the thermal scene and then the gas temperature fairly well. But given that, then this allows direct observation of those, the formation of those primary aerosols. And we've seen an SO2 to sulfate ratio that was controlled by plume temperature and observed rapid condensation of those aerosols in the direct line of sight, because we're really looking at plumes really, really close to their source here, only a few seconds. And seen some gradual changes in plume characteristics over fairly short timescales. And so this new method could provide a way to quantify SO2 to sulfate ratio at the source, which would have some would be helpful for further atmospheric dispersion models, which are used to forecast health hazards, for example. And as well, this type of data could be used to link changes over short time scale in gas composition to other monitoring signals, such as the harmonic tremor, but deformation or thermal flux, and others could be as well compared to if the data is acquired over a long enough time scale. And so if I can leave you with a take-home message, is that I hope that I've shown you that there's a wealth of information, those open path FTIR spectra, that has been to some extent untapped, and that improving those retrievals in a few different ways can create new use cases and maybe enhance the science return that we get from not only the data sets that will be acquired in the future, but also potentially looking back at the data that has already been acquired. So the emission geometry opens up the possibility of long-term continuous monitoring, and as well possibility of applying open path FTIR to plumes from more explosive eruptions. And this ability of retrieving particulates in both cases can enable us to look at plume evolution in the first few seconds and minutes of the lifetime of a plume, and quantify these aerosol emission at the source. As well, this can be adding some context and inform potential sources of error for UV methods, namely the presence of particulates we know can be a problem when retrieving SO2 in the UV. And so with that, I will take some questions. I'd like to point out that I am coming to an end at my postdoc in Oxford, and I will be starting a position at Northern Arizona University. And so if you're interested in reaching out, collaborations or discussions, this is where I'll be able to be found in the near future. Thank you.
Thank you very much, JF. That was a fantastic talk. So yes, if you have any questions, please put them in the chat or the Q&A. We actually already have one already, which is from William Harbert, who says, "Thank you for this presentation. Is there a public access site for with the drone data sets?"
No. So I assume the drone data set is the ash sample. So it's not on a public repository. I'm trying to do that before I leave Oxford. However, if you reach out, I'm happy to share this data.
Great. So I have a quick question. You mentioned that there are some differences between the UV and infrared. I was wondering if you could elaborate on some of the reasons for this.
Yeah. So when looking at UV, the processes are different. It's scattering mostly, but there's a known effect of when particulates are present in the plume. This can introduce some over or underestimation of the SO2 retrieved with the method, and this is due to multiple scattering within the plume. And so one of the argument is that because we're using longer wave numbers and in the infrared, it might not be affected in the same way. And so I don't want to be definitive in this, but there might be a way to look at just how much to kind of look deeper with the infrared into the plume and be less affected by those kind of retrievals. And so this could be helpful. On the other side, there's pros and cons for both methods, and there's potential for cases where the UV is more appropriate or the infrared is more appropriate. And of course, this method here that I present is not as well established as those UV DOAS methods. So I'm not suggesting to replace one with the other at all.
Thank you. Do you know if there are any future campaigns planned using these methods?
Well, for the emission measurements, I know that Sandro, our collaborator at INGV, has taken several and is willing to do it. However, this does require like a pretty particular instrument that is calibrated, has those calibration targets, and so it's not possible everywhere. And it still does rely on somebody willing to take the instrument and go and do the acquisition. There's no real effort to deploy this as a monitoring tool just yet, but the potential is there. I'd like to go back and say if this is possible, and in the future, yes, there's plenty of other places where this would like to be. I would like to develop this. Yes.
Yeah, I would definitely like to see more results using this method.
Yeah, more data is definitely what is needed.
Okay, we have a talk from Michael Ramsey, who says, great talk. How does your software and results react to different viewing angles into the plume? And can you do transects in real time? Right.
So I assume this is talking about the emission measurements. And in this case, it's very, very sensitive to the viewing angle. And so transects, we've tried to do transects, and it's not really straightforward, because essentially we need to rethink all of our model and all of the reference kind of cross sections that we establish for each viewing angle, and so that makes the software no longer kind of near real time. But in theory, it is possible to do this. However, the question becomes the magnitude of the error if we don't estimate the viewing angle properly, could become quite large. And if it's larger than the change in the SO2 retrieved, then that could become a problem. But in theory, it is possible.
If there are more questions, could you please ask them in the Q&A? We have another question from Eve Grant, who's asking what the detection limits are like for SO2.
Yeah, that's an interesting question, and it's kind of a hard one to answer, because one would like, perhaps you would like some numbers in terms of concentration or column density. Really, it depends on the thermal contrast between the plume and the atmosphere. And so for those measurements that we've taken, I think the column density was maybe, I can't really say for sure. I'd have to go and look back, but it's quite sensitive, as sensitive as the UV method for the configuration we were looking at Stromboli. This may not be the case in different scenarios where the atmosphere behind the plume might be warmer, for example, or the plume itself might not have such a thermal contrast with the atmosphere, and then it becomes more difficult to do that, and the detection limit then goes up.
Okay. Another question is, how does distance from the plume affect the emission measurement in terms of UV versus infrared methods?
Yeah, so that's another source of potential contamination that is in the UV measurements, is the light dilution, this light dilution effect. And so further away from the source becomes more difficult because that light dilution effect becomes more important. In the infrared, I would postulate that perhaps we are less sensitive to that to a point. And so that the the window is fairly transparent within the infrared, and so even at greater distances, we can still get a measurable signal. The controlling factor again is the thermal contrast between the plume and the background here. And so colder backgrounds and warmer plumes is what is needed in this case. But I think perhaps this method is less affected by that and could be used at longer distances in theory. Then again, I haven't tested
it. Okay. I think we have hands up from Taja Roberts. I think we're going to try and let her speak.
Yes, I allowed him to speak if we can.
And if anyone has any other questions in the meantime and wants to put them in the chat. Getting lots of questions now. Okay, so move to the next question. Would emission measurements work if you had fog or clouds between the plume and instrument?
So yes, short answer is yes, depending on how much fog and clouds. So it will introduce some additional scattering. So the problem is that you're then introducing a new source of aerosols, and so in that way, I'm afraid it might be limited as well. So in theory, there will be a measurable signal where UV would see nothing, but then you're introducing a new source of aerosol scattering, which then you must account for, and there's a lot of unknowns there. So that might be difficult.
Okay, another question from Charles Forrester, who says, thank you for the presentation, very interesting. What is the actual optimal plume distance ranges for the best results?
As always, I guess the optimal, the ideal plume distance is 0, but a few kilometers, I think, is perfectly reasonable, and that's what we've been dealing with in both emission and transmission cases, and it's been working really well. So that's also one of the strengths of the method, is to be able to make those measurements at a safe distance without having to risk equipment and or personnel.
Okay, a few more questions from Eric Alconado. How does measurements on higher humidity, how do measurements in higher humidity environments affect your results?
Yeah, they're definitely more challenging there. In theory, there's more absorption by water vapor, but again, this thermal infrared window is fairly transparent in there, and so as long as we have a good representation of what the temperature and what the humidity is in order to account for it in the model, then that shouldn't be an issue.
Okay, and then from Rebecca Galbraith, what model assumptions would have to change when scaling to explosive eruptions with denser or more ash-driven plumes?
Right. So this is something we haven't tested, but even in the Stromboli data sets, we can see that when there's a large amount of ash, there's a lot of large particles, and those particle sizes cannot be retrieved with these wavelengths. And then, of course, for the very large explosive eruption, this would be quite problematic, because as soon as the plume becomes opaque, then we can't really retrieve any of that information anymore. And so then it becomes the same as it would be with UV methods, which is moving the instrument downwind to a place where the plume is diluted enough to be transparent, and then or at least translucent, and then retrieve the properties further downwind.
Okay, so now a question from Tata Roberts, which is, what can you say about the temperatures of various gas emissions?
Right. So this is the part that was really interesting when we look at our data set, was that temperature dependence. And so what we hope that we're capturing in this data set is essentially like this kind of condensing of the aerosol, the formation of the acid, the sulfuric acid from the SO2 within the really hot part of the plume. And then as we're capturing more and more of the cold plume, then we're looking at this phase then turning from gas to aerosol. However, in terms of capturing the temperature itself, that's not trivial. And one of the problems is that we don't know the temperature of the source. And so what we can guess, though, is the measure of the relative intensity of the gas versus the source. And so if we had additional constraints, so for example, from thermal cameras on the actual temperature of the source within our field of view, we might be able to say more about the true temperature of the gas. Right now, it's kind of just a number that shows the relative temperature of the gas, but it's one number representing a very complex scenario with temperatures profiles of only a few meters going from eruptive temperature to atmospheric temperature. So it's like it's hard to place some quantitative numbers there, but so far that's what we have. Yeah.
Great. So probably our final question today is from Santiago Arenello, who says, "Nice work. Have you compared your results with any satellite retrievals in Iceland?"
No, I have not. That's an intriguing thing. I imagine that you would mean in terms of the aerosols, and so yeah, or the SO2. We don't really get fluxes here. We only get kind of the composition at the source. But it would be interesting to look at those aerosols where they're formed and further downwind. There's also a number of direct sampling studies that have come out, or I know will come out soon, with some drone measurements at the site of the eruption and further downwind in Reykjavik. So those would be interesting comparison. I assume that's what you meant in terms of comparison with satellite, but I'm not sure.
That would definitely be something interesting in the future. So I think we'll finish there. Thank you very much, GF, for answering so many questions and for your fantastic talk. And I suggest that if anyone else has any more questions, to send an email. And before we finish up today, I wanted to give another quick reminder that we have the next COMET Plus webinar next week at the same time as this one. So we hope to see some of you there. And if anyone wants to catch up on previous COMET webinars, you can do that by looking at the recordings on YouTube. So thank you again, JF, and thank you all for coming, and hopefully see you at future webinars.